Hey class, this is Ms. Roberts at Shasta High School, and I'm glad you're here this weekend. I was trying to keep this brief, but the goal is for us to go over the Chapter 1 tests and help you go through and do test corrections in preparation for a test recovery quiz next week. And so my expectation is that you go through and any problems or you missed points, you come through and do the problems with me, so to speak, and watch them. So the first question here, we've seen enough, and the question is, does this relationship appear to be a function? And at this point, I think I want to contrast, like, well, what would a non-function look like? And this is a great example, right? So you can see, for example, if I was to give this a value of, let's say, x is whatever this box is, the thing is if, let's say that this is 3, when I give this 3, right, you can see that there's one possible y value here, and there's another possible y value here. So we would say that this is not a function because that particular x input has two different outputs. So a relationship is a function if for each x there is at most one y. So for this particular one, I would say, does this relationship appear to be a function? I would say yes. And to explain what is necessary, I would say each y value may have at most, because sometimes it's got nothing, but it can have at most one x value, right? So sometimes there's things that aren't in the domain, but if each, I got that backwards, each x value, each value in my domain may have at most one y value. How did I do that so early on that I would have gotten those backwards? Normally if I'm tired, I could understand it, but I'm not tired yet. So again, the domain, right, are those x values along the x-axis that I pick and I put into the function. And if I pick an x value and I can see that it has two different possible outputs, it's not a function because a function may only have at most one output for an input. Next question says, what appears to be the domain of this function? So if I look at it, I can sketch it, right? The domain is looking like it starts here at 2 and goes all the way up. Let me see. And produces outputs until the number 9, right? So the domain of this function appears to be all the x values starting at -2 and going all the way up to 9. And what are they? They're the x's. So this is one way you can write it, right? The domains are all those x's that are greater than or equal to -2, but less than or equal to 9. But you can also just write it in words. You can say all x values from -2 to 9. And at this point, at this early on in Math 1, I'm okay with not even being really particular about whether or not the endpoints are included or not. The range then are all the possible outputs. So if you look at this function, right, I could never get an output of -1. I don't care what value I pick from my domain. I'm never going to get an answer back of -1. In fact, the smallest answer that I'll ever get back from this function is I could get this, right? I could get a smallest answer of 2, right? And in fact, when x is 6, when I give it 6, I would give that smallest value. So the smallest value I could get would be 2, and it looks like the very largest value possible would be the number 9. So the range of this function, right, the allowable outputs or the possible outputs, look like everything from 2 up to and including the 10. So I would say here, my range is everything from 2 up to 10. And again, those are my y values. Everything from 2 to 10 is a part of the range of this function. A couple more questions here. This one says, what is the value of f of 2? So if I give this function an input of 2, what does it give me? Well, when 2 goes in, this function appears to give me an answer of 5. So I would say f of 2 is 5. Right, like this, I said, when I give it 2, it gives me back 5. Also, when I give this function the number 8, when I give it an input of 8, it appears to give me an output of, let's see, 8 goes in. If 8 goes in, it looks like it's giving me a 4 out. So f of 8 apparently is the number 4. Oops. And then the other thing here is, this one's kind of backwards. It says what value or values of x will make f of x the same as 2, will make it produce an output of 2. Well, actually, I know that because we've already looked at it. Right? The only value, these are all the outputs of 2, and there's only one way that can happen, right? That happens when x is 6. It appears that I get an output of 2. So if I give this function 6, right? So when x is 6, f of that x, f of 6, will produce an output of 2. So this was saying I want an output of 2. What do I put into it to get that? So in this case, x. Next, rewrite and regroup the factors of the expression so that all giant ones are clearly visible. So I do want to point out there's a big difference between factors and terms, right? Factors are those things that are multiplied together to produce a product. And some of us are looking at this 36 and we're saying, oh, I can break this down into 2 different terms. The problem is we can't cancel common terms. It's not a thing. It doesn't work. The arithmetic doesn't work. So we need to factor this. And if I think about the number 36, I can certainly factor 36 as 3 times 12. So if I was to create some giant ones here, I could say, look, I'm going to rewrite this. I'm going to rewrite 36 as 3 times 12. And then in my denominator, you can see there was a 12. So just looking at these numbers, right? I've got the 36 is taken care of, and the 12 is taken care of. I've accommodated, or I've accounted for both of those. So my numerator has 36, my denominator has 12. The reason why I like this is because I can see, oh, this is 1, right? So this is not necessary in my answer. Multiplication by 1 doesn't change a thing. So I can get rid of that. Now that I look at the next part, I can see I have 8 factors of x in my denominator, and I've got 3 factors of x in the numerator. So I'm going to choose to rewrite this as x to the 3rd in the top and the bottom. I'm going to multiply that by x to the 5th. So if I look closely here, my denominator has a total of 8 factors of x, right? It's got 3 factors and 5 more. So it is x to the 8th. But again, what's convenient is now I've identified yet another giant one that can be gone, right? And then the final one that I recognize is in my numerator, there is this y squared. I'll just write that times a y squared. But in my denominator, I've got a y squared times another y because there's a y cubed there. So I rewrote the y cubed as y squared times a y. Again, it's not magic. If you look at the top, I've got 3 times 12, which is 36. I've got x cubed and I've got y squared. In my denominator, I've got a 12. I've got an x cubed and an x to the 5th. And I've got this y cubed. So basically, at this point, I've accounted for all the things that I can get rid of, all the giant ones. Right? So this is gone also. In my numerator, and I guess this is really probably I should have written this up here. In my numerator, if I look at my final results, my numerator has just the value of 3. That's all that's left in there. And in my denominator, I can see that I've got an x to the 5th power, and I've also got a y. So this is the simplified version of this expression, and I obtained this by identifying the giant ones and eliminating them. Let's move on to our next page. So for this one, we're instructed to simplify the following expressions, and our answers may only have positive exponents. And again, to simplify, what we're doing here is we're trying to reduce the complexity, reduce the number of operations needed to evaluate an expression. If I take a look at this, I can see that I am raising to the 3rd power part of this. In fact, this right here is being raised to the 3rd. And because of that, I can write 3 of those out. So I'm going to go ahead and just, for a reference, I'm going to write the 3x squared, right? So I've got, this is the same as, here's the 3x squared. That was part of this right there, the 3x squared. But then I'm also going to include these factors. I've got a 2x squared, another 2x squared, and a third 2x squared. So all of these factors, right, are coming from the fact that this was raised to the 3rd power. So now that I have all those listed out, I can say, okay, what's my answer going to look like? Well, I've got a 3 times 2, which is 6, times 2, which is 12, times another 2, which is 24. So numerically, right, I've got 3 times 2 times 2 times 2, 3, 2, 2, 2 is the number 24. And then how many factors of x do I have? Well, I've got 1, 2, 3, 4, 5, 6, 7, 8. So my answer is 24 times x to the 8th power. Let's look at the next part. The next part, I've got something's getting squared, right? This particular value of 2, this particular value 2 is not being squared, right? It's not included in the parentheses. What's being squared is the AB or 6b cubed. So if I was to expand this out, I could say, well, there's the 2 that I started with, but then I've got a 6b cubed and another 6b cubed. So there's 2 of those. So there's my 2 6b cubes, and there's this 2. Well, 2 times 6 is 12, times another 6 is 72, or said another way, right? 6 times 6 is 36, times 2 is 72. So I've got 72. And then how many factors of b do I have? Well, I've got 1, 2, 3, 4, 5, 6. I've got b to the 6th power. Now, as we do these, as we write these down, I hope you're paying attention to and thinking about shortcuts, because I think at a certain point I get to where I just can look at these and know what it is. But I want us to think about why things are what they are and work on that. Let's go to C. On C, I've got 24 in the numerator and 6 in the denominator. 24 is definitely, let's see, that's 4 times 6, isn't it? So if I want to, I can break that up as, I'll go 6 times 4. And then in my denominator, I have a factor of 6. Then I'm going to take this x to the 10th, and I'm going to rewrite it as x squared times x to the 8th. And on my numerator, I'm going to place an x to the 8th. So again, as I look at it, yes, the top is 24x to the 8th. Yes, the denominator is 6x to the 10th. And I can clearly see the value of 1, right? 6 over 6 is 1, and x to the 8th over x to the 8th is 1. So in the numerator, I'm left with a 4, and in the denominator, I'm left with x squared. So that's the answer I was expecting to see for part C. For part D, I've got, let's see, 14. 14 is 2 times 7. I know it's tempting to say, oh, that's 7 plus 7. Don't do it. We need factors. So 2 times 7 is 14, and then the denominator there is a 7. And then I'll break up the x cubed. I'm going to write that as an x times an x squared, and in the denominator I've got an x. So at this point I can see this giant one of 7x over 7x. If I want, I can grab it at once. Across the numerator, I can see that there is a factor of 2, and I also see that there are 2 factors of x. So I write that this is 2x squared. A single factor of 2 and 2 factors of x. Next, which expressions below are equivalent to 4x to the negative 2nd power? So thinking about this x to the negative 2nd and the reciprocal relationship of that, I think it's probably a good idea to think about, well, what the heck is that, right? So if I was to simplify that, that would be 4 over x squared. We're certainly going to talk more about how to deal with negative exponents in future chapters, but for now, I know that when I see a negative power, I know that it's a reciprocal. It's not a negative number. So instead of being x squared in the numerator, it's x to the negative 2nd in the numerator. It's the same thing as 1 over x squared. So this is what I'm looking for. This is my target. I'm trying to find any and all expressions that are equivalent to this expression. If I look, well, A is just screaming, pick me, right? Clearly this is 4 over x squared. They're exactly the same. 1 over 4x squared is not the same, because 4 is not the same thing as 1/4. So I can say, well, B, you're not playing the game. You're gone. C, it turns out that I've got this 16 in the numerator, which is 4 times 4. And in the denominator, there is a 4 times x squared. So in this case, you can see that I have a giant 1 of 4 over 4, right? There's that common factor. So I'm left with 4 over x squared. So I would say that C is also the same. D certainly looks promising because I can see the x cubed and the x to the 5th is going to give me an x squared below, right? And if I think about the 12, that's a 3 over 3 times 4. The problem is when that giant 1 is gone, right? This is just 1 over 4x squared, which is the same as B. So this is not making the cut. The square root of 16 is 4, right? So if I look at this, this numerator can be written as 4 times x squared, or I could flip it if I want, x squared times 4. And in my denominator, I've got x squared. And if I highlight that by grabbing that and kind of pulling it out like that, you can see I'm left with a 4 in my numerator and an x squared in the denominator, which is again the target that I'm looking for. So this is also equivalent. And then the last one, negative 8x is not, right? And to be honest, sometimes when we look at these negative exponents, some of us are inclined to think that somehow it makes a number negative. So it's not as goofy as it looks. I can understand, where an answer like that could come from. Let's look at question 5. It says of the 6 points below, 5 rather, of the 6 points below follow the same pattern. 1 does not follow this pattern. Use any method you wish to determine which point does not fit this pattern and show your work. So I call it a couple different solutions. One of them that I saw often was creating a different representation. Instead of having this list of points, some people built a table of values. So I can see that there's x values and there's y's. There's a -3. I don't have -2 or -1, but I do have a 0. -3 gave me -11. 0 gives me the number, let's see, 0 gives me the number 1. 1 gives me 5. I don't have a 2, but 3 I'm told gives me 13. 4 I'm told gives me 19. And 5 I'm told gives us 21. So if I look at this point here is kind of important to me because I can see that x is increasing by 1 and y is increasing by 4. So if I look at that change in y is 4 and the change in x is 1, I can see that this is growing by 4. So if I was to extend that pattern, I could say, well, 5 plus 4 would give me 9. 9 plus 4 would give me 13. 13 plus 4 is problematic, right? When I take 13 and I add 4, I land at 17, right? So if my pattern is adding 4 each time, I would expect to see a 17 there. And in fact, if I go one step past that, 17 plus 4 does give me 21. So I'm liking this pattern for all of these, right? Except you just highlight this one here is suspicious, this 19. Also, if I went backwards, right? If I took -1, I'm sorry, if I took 1 and I subtracted 4, right, 1 minus 4, I could infer that this should be like a -3. And if I subtract 4 from that, I'm at -7. Whoops, -7. -3 minus 4 is -7. And then -7, -8, -9, -10, -11. Yeah, all of these follow this adding 4 pattern, right? Except this one value here. So I would say that the point, so I would constitute this as showing work. And I would say that the question is which point doesn't fit? And I would say the point 4, 19 does not fit. And then it says, use a second method to verify your answer. Well, geez, one of the things I guess I could do is I could also look at this as an equation because I know my 0th term. I know my 0th term, and I also know that my growth is 4. So I could write y is equal to 4x plus 1. Is that right? 4x plus 1. So I could say all values in the table can be generated with this rule, except, right? I'm off the page, except for 419. I'm having an issue here. It keeps grabbing this invisible 419. 419 does not work, right? 4 should have went to 17, not 419. But you can see if I grab any one of those x's, multiply it by 4 and add 1, I'm going to get the corresponding y value, except for that one. Definitely an open-ended question. I got a lot of interesting things, a lot of different answers, and I really didn't count. I wanted an explanation, right? So I wanted you to explain how what you were doing was verifying that 419 didn't fit, and you needed to identify 419. All right, question number 6 has 4, I think, pretty straightforward linear equations we're going to solve. And I'm just going to go through some standard things that we might do. So I'm just going to rewrite this as 5x plus 2. And then I'm going to rewrite part of this using the simplest form of what we call the distributive property. So I'll write this as 3x plus 6. That's going to equal on the other side. If I distribute here, I've got 8x and then plus 8. So if I collect up some like terms on the left-hand side, I've got 5x and 3x, which is 8x. And I've got 2 plus 6, which is also plus 8. On the other side, I've got 8x and then plus 8. And what I could do at this point, I could go any way I wanted, but what I'm noticing is that I have exactly the same thing on both sides. And honestly, if I think about it at this point, it doesn't matter what I pick for x. It's going to give me the same value on each side. So if I stopped here and I put x as 1 on both sides, you can see that becomes 16 equals 16, right? If I hit x is 2 times 16 plus another 3 times 8 is 24. I get 24 as 24. If x is 0, I get 8 equals 8. So what's happening, right, we've kind of collapsed this down to an identity. It's something that's always true. I could take away 8x from both sides. I get 8 equals 8. That's always true, right? It doesn't matter what x is. So what we say is that our solution is all real numbers. Any number you can pick would work. Those of you that are telling, and that's the solution. You were asked to solve. So a solution is all real numbers. Any one of those things works. Because that's what a solution is. It's a value that works. When you tell me infinite solutions, that's nice, right? But you're telling me how many solutions there are, not what a solution is. So when you tell me all real numbers, you're saying what a solution is. If I look at B, I'm going to again use this thing I call the distributive property. I'll rewrite this as 8x plus 5 equals 6 times x minus 18. I think what I'll do next on each side of this is I'm going to go ahead and I'll subtract 6x. So I like to write this down, and I very rarely write down what I'm doing. I will just do it. And then in my mind, I'll stop before I go to the next step, and I'll say, what did I just do? And I'll remind myself, okay, I took away 6 of the x's. I took away 6 x's from the left, and I did the same on the right, and this is what I get. Next, I'm going to go ahead and I'm going to subtract 5 from both sides. So if I subtract 5 from this side, I'm left with just 2x. And when I subtract 5 from 18, negative 18 rather, when I take away 5 from negative 18, this is going to become negative 23. And then my answer then is what I get when I take and I divide both sides by 2. So my answer is negative 23 halves. And that can't be reduced. There's no giant ones there, right? No common factors. So I'll just leave it like that. Negative 23 halves. Next problem, same deal. Let's see. I guess, let's see. I could do a lot of things first, but I don't like the parentheses here. So I guess I'm going to choose to go ahead and rewrite the left-hand side using this thing called the distributive property. So I've got 8x plus 12, and then minus 5x. And when I distribute the negative 5 with the 3, I get a plus 15. Then I've got a plus 6 equals 42, and then minus 6 times x. Let's see. I've got 8x and negative 5x, which is 3x, and I've got a 12 and 15, which is 27. That doesn't feel right. It is 27, and then there's a 6, 27, 28, 29, 30, 31, 32. Okay, so I'll just do 12 plus 15 is 27, and 27 plus 6 is 33. And on the other side, way over here, I've got that equals 42 minus 6 times x. I guess the next step for me, let me just write it, and then you can think, what did I do? Yeah, I hear you. You said, Mr. Roberts, you just added 6 values of x to both sides, and I did, to the left and right. Now I'm going to go ahead and I'll write it, and you tell me what I did. What did I do to both sides? Well, I'll tell you what I did. I subtracted 33 from both the left-hand side and the right-hand side. What am I doing to both sides? Well, I'll tell you what I did. I divided both the left-hand side and the right-hand side by the number 9, and I got that x is 1. Last problem in this set. Let's see. Nothing to distribute here. That's nice. So I'm going to write this as negative 3x plus 5 equals 3x plus 12. I'm going to do this to both sides. What did I do? What did I do to both sides? I'll tell you what I did. On both the left-hand side and the right-hand side, I added 3x. I added 3 x's. What am I doing to both sides? I'll tell you what I did. On both the left-hand side and the right-hand side, I subtracted the number 12. Both of them were decreased by 12 units on each side. What am I doing to both sides? I'll tell you what I did. I divided both the left-hand side and the right-hand side by 6. When I do that, I get x is negative 7/6. Now, having an answer like that and being confident in an answer like that is always kind of a, it's a bit of a mystery. So I want to show you something I might do. I might grab my calculator and enter a fraction with a negative 7 in the numerator and a 6 in the denominator. That's certainly negative 7, 6. And I'll just press enter and leave it on the stack. It's right there. I can go up and get it if I want it. And then I'm going to check that. Does it really make both sides of this equation the same? So I can say, hey, this is the opposite of 3. I'm just reading what the equation says now. It says the opposite of 3 times, go get x, right? Gotcha. Plus 5. So when I do that, when I enter the opposite of 3 plus 5, it gives me that this side of the equation is 17 halves. 17 halves. Now, on the other side of the equation, you can see what I have. I have 3 times x. Okay, let's try that. I'm going to go 3 times. I don't have to enter it again. I just go up, up, up until I got it. There it is. 3 times negative 7, 6. And then I'm going to say plus 12. Huh. Did you see that? That's exactly what I wanted. It's very clear that both sides of this, although my pen is a mess, become, the green is too bulky. The green pen is not as, the green pen is not 12/2. So both are 17/2. So when x is negative 7, 6, right? When this is my x, it does make both the left-hand side red and the right-hand side, the green side, equal to 7/12. So that is indeed the solution to this equation. Okay, last question on the third page, number 7. It says for the functions, and I give you two. I define what f of x is, and I define what g of x is. F of x takes an input, and it doubles it, and then it subtracts that result from 15. You can see f of x is 15 minus 2x. G of x takes its input, squares it, and then adds 5. So if I evaluate these functions, I always like to use this notation. So I'm like, okay, I want f of negative 4, and that equals 15 minus 2 times a place for the input. So what's being placed in this function is negative 4. So negative 4 lands right here. So what I have now is 15 minus 2 times negative 4, which is 15 plus the number 8, which is 23. So when this function gets negative 4, it gives me back the value 23, right? Negative 4 goes in, 23 comes out. Let's look at g of 2. So for g of 2, right, you can see that's going to be in parentheses are important to me. A place for the x, I'm going to square whatever the x is, and I'm going to add 5. What's going in for x, you say? Oh, don't be ridiculous. It's right there. 2 is going in for x. So this is going to be 2 gets squared plus 5. 2 squared is the number 4, plus 5 gives me 9. So when 2 goes into g, it gives me back a value of 9. And I'm also asked for what is f of 10. So f of 10 is what? Well, it's 15 minus 2 times that input. Here's the 10. No, not that pen. Not that pen, just the number 10. There we go. Well, 15 minus 20 is negative 5. So when the value 10 goes into f, it produces an output of negative 5. And the final problem is g of two things. So I need to know the sum of two things. So one of them is f of 5. So let's do that. So that f of 5 is 15 minus 2 times the input, right? So you can see what I've just written here is that's exactly what the definition of f of x is. It's always 15 minus twice x. So you can see I've got the 15 minus twice x, 15 minus 10, which is just the number 5. So that's the f of 5 bit of it, but I need to add to that, right? There's an addition problem here. I need to add to that whatever g of negative 3 is. So g of negative 3 looks like this, and this is where the parentheses are really important. It's going to be whatever x is squared and then plus 5, because I need to square x, right? Squaring x in this case means I need to square the negative 3. And I think I've talked about this in class. If you look at these calculators, they do these exactly right. So the notation matters. If I was to enter the opposite of 3 squared, right? This calculator is going to say negative 9 because that's what the opposite of 3 squared is, right? That's not what we have here. What we have here is that x is getting squared and playing the role of x is negative 3. So I need to show that negative 3, there it is, the whole thing, negative 3 gets squared. And when I square negative 3, I get 9. So for this problem, we're looking at 9 plus 5, which is 14. So what we're looking at is 5 from f of 5 plus 14 from f of negative 3. When we add those two values, we get 19. So our answer there is 19 for part D. And now on to our final page. There are 3 numbers here. We're asked to write each of these numbers in scientific notation. It turns out none of them are actually in scientific notation, right? So we need to write them in scientific notation. And remember, scientific notation is what? The scientific notation is always the product of two things. One of them is a power of 10. So 10 to some power, I don't know, I'll just say b, right? There's a power of 10, and it's multiplied by a number n that is in a very specific range, right? It can be 1, right? But it has to be less than 10. So it's anything 1 or larger than 1 all the way up to 10. So that's what, so I could write it like this. It's those two things. Well, I can see this first number, 435.2 is not such a number. So what I'm going to do is I'm going to place the decimal value where it should be if it had the right form, right? That number. 4.352 is in the right location. Now, it turns out that that number, 4.325, is not the same as 435.2. So what I do is I'm going to multiply that by 2 factors of 10. So if I multiply this number by a 10 and another 10, right, this number becomes exactly equal to 435.2. So I'll underline this in green. These two things are exactly the same now, right? 435.2 is the same as 4.352 times 10 to the second. Now I need to multiply by 2 more additional factors of 10, so I'm going to go times 10 squared. At this point, right, we just need to clean this up because I can see how many factors of 10 I need. There has to be 4 of them. So I'm just going to say that my answer is 4.352 times 2 factors of 10 times 2 more factors of 10, which is 4 factors of 10. Right, the next one seems maybe a bit more straightforward. Again, I'm focusing on getting a number that's in the right range. So 1.3 would be such a number. Unfortunately, 1.3 is much larger than the value I had above, right? You can see I only had 0.0013, and I've turned this into 1.3. Well, in order to make the 1.3, I have to make it smaller. So to make the 1.3 smaller, what I'm going to do is I'm going to divide it by some tens. And remember, when I divide by 10, I'm looking at 10 to the negative first power. So I've placed the decimal here. This is 1, 2, that's 3 factors, or 3 times I would have to divide by 10. So if I have 1.3 and I divide by 10 3 times, right? Divide by 10 3 times. What do you mean divide by 10? That's the same as me going like this. Times 1/10, times 1/10, times 1/10. That's me dividing by 10 3 times. Those numbers will be exactly the same. But because I need factors of 10 and not factors of 1/10, I just recognize, oh, those factors of 10 are all 10 to the negative 1. So I need 3 of those, right? That's 3 of the 10 to the negatives 1s. So the thing that I'm underlining here, right, these two things are exactly equivalent to each other. Check them out on your calculator. Plug in some numbers and play with them and see that, yeah, 10 to the negative first is really 1/10. If you take 100 and multiply it by 10 to the negative first, you're going to get 10 as an answer. So that's it. That's my answer there, right? It's the right form for the value n, the 1.3. And then I'm multiplying that by some powers of 10, 10 to the negative third. The last question, I write down 1.23. I know that this is too small now. The number I've written down is small, right? The one above was larger. So this time, instead of multiplying by negative powers of 10, I have to have this equal. This has to equal this. So I'm just going to multiply by powers of 10 until it's equal to it. How many of them? Well, it turns out if I multiply by 1, 2, 3, 4, 10 to the fourth power, it'll exactly equal it, right? If I take, and it's probably worth it to look at my calculator. Where's the calculator? There it is. If I look at this calculator and clear it, oops, I can take 1.23, and if I multiply it times a 10, what is it? What do I get? I get that. If I multiply it by another 10, oh, I thought it would repeat it. I can do this. I could say, oh, here's what I want to do. This is the best way to do it. 1.23, enter it, and then you just say times 10. This is nice because it takes the previous numbers and multiply it by 10. So there's 1 10, 2 10s, 3 10s, and 4 10s. So if I take 1.23, and if I take the 1.23 and I multiply by 4 factors of 10, you can see there's like 1, 2, 3, 4 factors of 10. I get exactly 12,300. So this number, 1.23, times 10 to the fourth is the number in scientific notation.